All right, good afternoon, everybody. Welcome back to Intro to Physics, lesson number 3. So we are going to jump back in where we left off yesterday. Remember yesterday we were talking about units and how to convert between units, the metric system, all that jazz. And so I left you off with a bonus question, like a challenge problem to do. And so we're going to start off today by going through that bonus problem. All right, can you guys all see my answer to the bonus problem?
Yes.
Great. Okay, so this was our bonus problem, finding the mass of an asteroid that has a radius of 3.5 kilometers. So we were then told to express the mass in terms of cruise ships. Okay. So I gave you a couple of conversion factors there. So a metric ton is 1,000 kilograms. 200,000 tons is one cruise ship. The density of the asteroid is 3,000 kilograms per meter cubed. And then we're going to assume that the asteroid is a sphere. So like I said, this was a challenge problem because there is a little bit of an extra step. It's not a straight unit conversion problem. So first we're going to start with this understanding of what density is, and that's the mass of the object divided by the volume. So since we were given the radius, we can find the volume, and we know that, well, we're assuming that it's a sphere. So the volume of a sphere is 4/3 pi r cubed. And then we can multiply that by the density to get the mass of the asteroid in kilograms. So our density is 3,000 kilograms per cubic meter times the volume of 4/3 pi. And then our radius was in kilometers. But since our density is in meters cubed, we need to convert that to meters before we can just plug it into our equation. So here's my little unit conversion piece right here. Okay, so I'm converting it from kilometers to meters and then cubing that radius. And that gives us a mass of 5.39 times 10 to the 14 kilograms. Of course, we weren't asked for kilograms, we were asked for the mass in terms of cruise ships. So then we have to convert it from kilograms to cruise ships using those other conversion factors that I had given you. And so our answer ends up being 2,690,000 cruise ships. A lot of cruise ships in this asteroid.
In scientific notation, it would be 2.69 times 10 to the 6th power cruise ships.
Yep. Okay, do you guys have any questions about this bonus problem? I'm seeing some head shaking. That's good. Okay. Well, then we will move on to the topic of the day, which is vectors. Woo-hoo! Man, I don't know about you guys, but I just love Despicable Me. I think it's a great movie. Maybe it's because I have 3 kids right now, but I feel like I loved it before that. So, no judgment there. But anyway, this topic of vectors is super duper important because we'll see vectors come up in many of the other topics that we study. We really won't get a break from vectors until we talk about energy, and then we'll jump right back into vectors with the next unit of momentum. So pretty much every topic within physics, at least physics 1 that we will go through, deals with vectors in some capacity except for energy. So we're going to do, I have listed here sections 1.7 to 1.10 in the textbook. We're just going to do 1.7 and 1.8 for now, and then we'll come back and do those other couple sections in a little while. All right, so vectors and scalars are often kind of talked about together because they sort of go hand in hand. They're both different types of quantities. So a scalar is a quantity that just has a magnitude or a size associated with it. It does not have a direction. So that would be things like time, mass, dollars, distance, right? We don't ever really talk about our class being an hour long up. That doesn't make sense. Time does not have direction associated with it for our purposes, right? Mass, same sort of thing. We don't have an object that's 2 kilograms west. It does not need a direction. Can you guys think of any other quantities that I don't have listed that are scalars? So they just have a size associated with them and not a direction. What are some other examples?
Volume,
Volume, good. Yes, I like it. Length,
Speed.
speed, good. Height, cool. Temperature, yes, awesome. Density as well, energy, right? These are all examples of scalar quantities. Okay. So when we use scalar quantities, the math is very simple and straightforward, right? So if we're just adding together two masses, for example, 6 kilograms plus 3 kilograms equals 9 kilograms. Great. And we know from yesterday that our units must be consistent with each other when we're adding and subtracting. And we can see there in that example, it is consistent. Kilograms plus kilograms equals kilograms. Right? Even when we're multiplying or dividing scalar quantities, the math is still very straightforward. 4 times 2 seconds is 8 seconds. Right? So that's nice and simple and good. Vectors go a step beyond that. So vectors are quantities that have a magnitude, a size, and a direction associated with them. So that would be things like displacement, right? Miami is not only 300 kilometers away, it is 300 kilometers south of Melbourne. Velocity, it doesn't just tell us how fast we're going, it tells us how fast we're going in a particular direction. Acceleration tells us about how the velocity is changing. So not just if we're speeding up or slowing down, but if we're changing direction, that's also acceleration because the direction makes a difference. Force, it matters to you if you are pushing on someone sideways or down the stairs, right? That makes a difference. So force is a vector. It has a direction associated with it as well. Okay. So when we're dealing with vectors, we represent them as arrows because arrows have a definite length, a size, and that arrowhead tells us about the direction. Remember, both of those aspects are important for vectors. So when we draw these vectors, we're going to measure the angles counterclockwise from the positive x-axis, just like we have in this picture down here. Right, so here's our vector. The length of it tells us the magnitude, and the direction is measured from this positive x-axis or from east, if you're thinking about cardinal directions. When we see a vector written out in the textbook, for example, usually we'll see it as either a bold letter or a bold letter with a little arrow on top. Those just differentiate between scalar quantities and vector quantities. When we're talking about just the magnitude of it, so just the size or this scalar portion of it, you'll see it as just a letter, so just A, or sometimes you'll see it as the absolute value of the vector, right? Because that just tells us about the size, and we don't care about the direction for the magnitude. Okay. So distance versus displacement. I think this is one of the parts of vectors that kind of gets confusing for a lot of people. Figuring out
Can I tell this one?
between distance and displacement. What did you say?
May I tell this one?
Sure.
Okay. So for like displacement, it is literally your starting place and how far you are from the finish, from like the place you're gonna be at once you like take the path you are going to take.
Mhm.
But the distance is like your actual path. So that's the difference.
Yeah, that's right. So we can see here in our picture down here, the distance takes into account the entire pathway that you travel, right? All of those pathways added together, the total distance is your distance. And the displacement is just like if we could draw a straight line from where we start to where we end up, that's your displacement. But remember, displacement is a vector. So we do need to have a direction associated with it as well. It's not just a number. We need the direction too. Right, so if I travel 5 meters to the left and then 4 meters to the right, you traveled a total distance of 9 meters, right? Add together all of those pathways regardless of the direction. But your displacement, how far you are from where you started, is just 1 meter to the left, right? That left is also important for your displacement. So that means if you go to the store and come back to your house, no matter how far away the store is, no matter how long your journey was, your displacement is 0 because you started and ended up at exactly the same place. Okay. Vector math can be a little bit weird to remember. Okay. So when we're dealing with vector math, it's not as straightforward. Lol. Because usually we'll do it graphically. So we'll draw out the picture of all of these vectors added together. You don't have to do it graphically every time, and I'll show you how to do it just straight mathematically as well. But if we're adding vectors together in a diagram, there are some rules that we need to follow. So first of all, we can slide our vector arrows around as long as you do not change their length or the direction that they are pointing. Right, so if I have a vector that's in this direction and this long, I can slide it to be wherever I want on the diagram, but it must stay this long and pointing this direction. Then we'll draw all of the vectors tip to tail. So picture your arrow, right? The tip of the arrow and the tail of the stem. So we draw all of our vectors lined up tip to tail. And then the resultant vector, or the result of adding them all together, starts at the tail of your first vector and ends at the tip of your last vector. That sounds very vague, and I will show you a simulation of that in just a moment. But our last rule before I show you that is that subtracting vectors is the same thing as adding a negative vector. So you can flip it 180 degrees. That's the same thing as making it negative or subtracting a vector. So this link that I have here at the bottom is a simulation. This group has all kinds of awesome physics simulations that you can really benefit from. So I highly recommend that you explore their website a little bit. But I'm going to stop sharing our PowerPoint and I'm going to hop over to this simulation just so we can check it out for a moment. Okay, so can you guys all see my screen called vector addition?
Aye.
Yes.
Okay, so we have all different ways, I guess, that we can play with vectors in here. So we'll start by exploring one dimension. And I'm just gonna place this arrow right in here, right? So here's our vector, it's called A. We can change the length and we can see up here, here's our magnitude symbol. That tells us how long our vector is. So right now it's 16 boxes, 16 units. It is at an angle of 0 degrees because remember our angles are always measured from the positive x-axis, and this vector is directly along the positive x-axis, so it has an angle of 0. Okay. If I create a vector going the other way, you can see now it's at an angle of 180 degrees. Same magnitude, but now pointing exactly the opposite direction. These numbers over here tell us about the components of the vector. So how much of this vector is pointed in the x direction and how much is pointing in the y direction. Right now, since all of our vector is along the x-axis, albeit the negative x-axis, none of our vector is pointing in the y direction. So we have a y component of 0. We have an x component of the entirety of the vector. Why wouldn't the magnitude be negative? That's an excellent question. Remember, magnitude just tells us about the size of the vector. It doesn't tell us anything about what direction it's pointing. And negative is a direction. So if we said the magnitude is negative 16, that's not actually the magnitude. That's the magnitude with the direction. So the magnitude itself, or just the size of the vector, just the vector's length, is 16 boxes, right? And its direction is negative, or negative x. So another question, would that mean that mass is a scalar and weight is a vector? Yes, it does mean that. Good. Because weight is actually a kind of force. It's the force of gravity pulling us down. And gravity pulls us down, which is a direction, right? So that is a vector. Good. Okay. Now there's only so much that we can do in one dimension. So I'm going to go back. And we'll do some two-dimensional. Okay, so here we go. We have our nice little grid. I'm going to drop in a vector. Bloop. This vector A is 10 boxes long in its magnitude. Currently, it's in an angle of 53.1 degrees. So we can change it around. We can change the magnitude. We can change the direction. And we can see that by doing that, we're also changing the components of this vector as well. So right now I have it set so that our vector is 11.2 boxes in length. It's at an angle of 26.6 degrees. And we can see, based on where the tip of the arrow lands, that it is going 10 boxes in the x direction. So its x component is 10. And it's going up 5 boxes in the y direction. So its y component is 5. Okay. Now, if we take a look at these numbers, 10 plus 5 is not 11.2, right? We can't just take these two components and add them together and say, oh, that's our magnitude. Nope, that's not how math works, unfortunately. So I'll show you in just a little bit how to do that sort of calculation. Enter trig. Woo! But I want to show you really quickly how we add vectors together graphically, right? I was telling you that we'll add them tip to tail. So when we drop in another vector, we'll put it in so that the tip of the first arrow meets up with the tail of the next arrow.
Oh, wait. I just remember. Like, don't you have, okay, can I explain what is happening to find the whole sum of everything?
Sure.
Okay, so to find everything, you need to break up these two arrows into their own separate vectors and basically find the sum of the vectors separately. Then, oh wait a minute, no, actually, I'm on the right path here.
You are on the right track. I'm very proud of you. And we'll get into that in just a couple of minutes, actually. But I just wanted to show you with this how we add vectors together. And that's just by dropping them in so that the tip of one meets the tail of the other. We can do that for any number of vectors that we have. Just make the tip of one the tail of the other. Sorry, I'm trying to move the chat out of the way real quick. And then our resultant, or the result of adding together these vectors would be a vector that starts here at the tail of A and points all the way to the tip of the vector where we ended up. That would be like our displacement, for example. So if we were walking around the neighborhood and we went this way and then this way and then this way, we are a displacement of this far away from our starting point, right? So that would be our resultant vector. Now we have a question in the chat. Is there a formula for finding magnitude, degree, or such Yes, there is, and we will get into those formulas in just a few moments.
If I remember correctly, to
Mhm.
find the sum of the vector, would you have to use Pythagorean theorem.
Yes, we will. Okay, I have another question in the chat. How is the angle negative 90 degrees? Remember, that's just looking at vector C here. And our angles are measured, right? So counterclockwise from 0 degrees would make it 270 degrees. This simulator just measured it downward, a negative angle. Both are valid, but this one is a little bit less common in terms of what you'll see angles written as. Okay. Well, let me stop sharing this screen. You can play around with the simulator on your own time if you would like to. But we're going to jump back into our PowerPoint. Okay, are we back at vector math? Yes, perfect, awesome. Victor, I can only see you, and I appreciate your head nods because I know that's how I know that we're doing good. Okay. Anyways. So like I was saying, vector components show us how much of the vector is going horizontally or in the x direction, and how much of the vector is going vertically in the y direction. So when we're dealing with 2 dimensions or 3 dimensions or any number of dimensions, we can break these vectors down into their components. And usually we'll call those x and y components, or x, y, and z if we're in 3 dimensions. So the way that we'll see that written out in a formula would be vector A equals its x component plus its y component. However, like I said, we can't just add those numbers together. We can't add the magnitudes together because these are vectors. The direction must enter in to our equation. So here is, if you've taken trig, you've probably seen this sort of thing before. This is how we write our trig identities as such. So how many of you guys have heard of SOHCAHTOA before?
Sine, cosine, and tangent.
Yes, good. Okay, so if you've heard of SOHCAHTOA, I mean, even if you haven't, SOHCAHTOA is just a mnemonic device to help you kind of remember how these trig angles are written. So here we have a triangle, and for this sake, it's a right triangle, and this is the angle right here that we're interested in, angle theta. This symbol is the Greek letter theta.
Oh, to find the angles in a right triangle, you have to use the reverse of sine, cosine, or tangent to find the angle.
Yes, we'll get there. So here's our angle, and since this is the angle that we're interested in, this is how we're going to kind of define which side of the triangle is opposite and which one is adjacent. Now remember, the hypotenuse of a triangle is always the side that's the longest. No matter what angle we're most interested in, the hypotenuse is always the longest side. But since we're looking at this angle right here next to A, adjacent means the side of the triangle that's next to our angle that we're interested in. And the opposite side of the triangle is the one that's opposite our angle, right? It's across the triangle from our angle. So the sine of our angle theta is defined as the length of the side that's opposite our angle divided by the length of the hypotenuse. So in our SOHCAHTOA, that's where those first 3 letters come. So SOH, sine is opposite over hypotenuse. The cosine of our angle is defined as the side that's adjacent to our angle divided by the hypotenuse. So that's CAH, C-A-H. Cosine is adjacent over hypotenuse. And then the tangent of our angle is defined as the side that's opposite divided by the side that's adjacent to our angle. So that's the TOA at the end. Tangent is opposite over adjacent. And so these three equations are going to be ones that you want to have memorized and ready, like at the tip of your brain, the forefront of your brain, however that phrase goes. Keep that in the front of your mind.
Oh, it's
go
the tip
through
of your
these
tongue.
sorts of vector problems. Did you have a comment?
Yeah, you were thinking of the phrase the tip of your tongue.
Yeah, tip of your tongue, front of your yes,
Oh.
whatever that thing is.
Mm.
Okay, and so this process works with whatever vector we're interested in: displacement, velocity, force, momentum, etc. There's a question in the chat: will we be using cosecant, secant, and cotangent? I will not be in this class, but you may need them later on. So it's a good thing to just be familiar with those sorts of identities. Yeah, it depends on the context. That's exactly right. Yes. Okay. So let's keep going. When we're expressing these components, so remember our x component, how much of a vector is to the side, and our y component, how much of a vector is vertical. There are actually quite a few different ways that we can write this down, and different ways that you'll see it written down in textbooks or on problems, homework sets, that sort of thing. So we might see it written in brackets in this way. And so the first number in our bracket would be the x component, and the second number would be our y component. And so that's one way to write it out. Here's another way we might see it. The top of this matrix is our x component, and the bottom is our y component. You might see it written out with the unit directions of I, J, and K if there are 3 dimensions. So the I direction, or I hat, sometimes is written as like an I with a little triangle hat on top. That's the x direction. And then the J, or J hat, is the y direction. And then K, or K hat, is the z direction. So here's another way that you might see it written as. There are those little hats too as well in this x and this y example. Sometimes you'll see it written out kind of separately in this way. So the velocity in the x direction is negative 4.92 meters per second. The velocity in the y direction is 18.4 meters per second. I will use this notation in a lot of my example problems.
I have a question.
Okay.
What does hat mean? What is you said before, but I couldn't really understand you. Can you explain what the little like carrots over the y and x means again?
Yeah, so that's just a way that we can differentiate in an equation between a direction x and maybe a variable x. Yes. Does that make sense?
Yes.
Perfect. And then another way that you might see vectors written is 19 meters per second at 105 degrees counterclockwise from east. So you'll see that this number out front, 19 meters per second, is completely different than negative 4.92 or 18.4, right? So that would be our magnitude of the vector, which takes into account both of those components. And then it tells you the angle explicitly there as well, 105 degrees counterclockwise from east. So when you're drawing out your vectors, this is a helpful notation for you. But again, you might see any number of these, or even some others that I don't have listed on here. It depends on the textbook, the professor, the situation, that sort of thing. Okay, so when we add components together, like I said, we cannot just add x and y together to get the magnitude, unfortunately. So when we have 2 or more vectors that we're adding together, the best way to go about it is to break it down into their components using those trig functions that we saw earlier, sine, cosine, or tangent, right? That will tell us about the length of whatever side we're interested in. And I'll go through some examples of that in just a couple minutes. So let's say we have two vectors that we're trying to add together and we have them written in this notation. Remember, the first number in the bracket is the x component and the second number is the y component. So when they're written out like this, it makes the addition pretty simple, right? We just add x with x. So 3 plus 2 equals 5. And we add the y with the y. So 9 plus -5 equals 4. And so this would be the components of our resultant vector, the result of adding together these two vectors. So our resultant vector has an x component of 5 and a y component of 4. Okay. So if we wanted to find then the magnitude of our resultant vector, here's where our equations come into play that you guys were asking about earlier. The way we find the magnitude of our vector is using the Pythagorean theorem. So we do our x component squared plus the y component squared. And then we square root that answer to get our magnitude. So 5 squared plus 4 squared, take the square root of that. We get a magnitude of 6.4, whatever units we're using. And to find the direction, the most common way to do that is using the inverse tangent. So that's tan with a -1 exponent. You might also see that written as the arctangent or a tan. It's the same thing, the inverse tangent. So when we have two lengths of our triangle, this is how we would find the angle that we are interested in from our trig definitions. So to find the direction, it's the inverse tangent of the y component over the x component. So the inverse tangent of 4/5 is 38.7 degrees. Now we can do this process for any number of vectors that we have. I mean, it gets a little bit tedious, but it's the same process. So just add together all of the x components separately. That will give you your resultant x component. Add together all of the y components separately. That will give you your y component to the resultant vector. So remember, we can always add x's with x's and y's with y's. We cannot add x's to y's. We got to keep them separate. If our vectors are in 3 dimensions and we're trying to find the magnitude, then you just pop an extra term, the z component, into your Pythagorean theorem as well. So the magnitude is the square root of x squared plus y squared plus z squared in that case. Okay, same process, just with an additional factor in there.
What about for the inverse of tan?
For 3 dimensions,
Yes.
we'll go through some examples of that in a little while. Okay. There's some questions in the chat as well. Is there a way to get x and or y when you have a magnitude and or direction? Yes, absolutely. Depending on what you have, will kind of determine how you manipulate those equations. And I'll try to go through a variety of example problems so you can see some different ways to manipulate those equations. Okay. So when we're multiplying vectors together, let's say we're multiplying a vector by a scalar, then we just multiply each component by that scalar number. So let's say our vector A has an x component of 3, a y component of 4, and a z component of 5. That means that 2a is just 2 times all of those. You distribute the 2 to each of those components. So it would have an x component of 6, a y component of 8, and a z component of 10. So multiplying a vector by a scalar is a pretty simple thing to do. If we're multiplying a vector by a vector, that gets quite a bit more complicated. And there are a couple of different ways that we can do that depending on the particular scenario. Those
Are we going to use matrices?
Cross products. What was your comment?
Are we going to use matrices?
I do introduce matrices a little bit, yes. So we'll get to that later. That's a little bit of a step up from where we are right now.
What is the practicality of multiplying a vector by vector?
So okay, so if we have like, here's an example from physics 2, just because it's in the front of my brain. Okay, so if we're dealing with the force that is created by electric charges together, right? So electric charges have a charge. Usually, if they're in the presence of a magnetic field, they are also moving. So magnetic field is a vector, velocity is a vector, force is a vector. And so when we're trying to find the force that is exerted by these charges, that would be QV, so the charge, which is a scalar, times the velocity, easy enough to do, times the magnetic field, right? So just that equation, QVB, we have a vector velocity times a vector magnetic field. And so to find the force, we do QV cross B. That's a cross product. And so we'll get into all of these like crazy right-hand rules and like figuring out the directions and making these weird like gangster signs. If you haven't seen those yet, they're pretty
Oh, the spin of electrons.
Yeah, so that would be one example of a cross product. Just that equation has several vectors in it that we multiply together. And we need to have a way to do that. And that's a cross product.
I also have one, like, I know you just brought up an example. Can you, like, do you have an example in like more Newtonian terms?
Ooh. I'll get back to you on that.
Okay.
Okay.
Big word.
Like a billion equations rattling around in my head, but I need to like narrow it down to a cohesive thought. Okay, a question in the comments. Cross and dot products are just trig, right? Yes, in a sense. But you can write them in terms of matrices as well, which is linear algebra. So that would not be trig, but there is a way to write them using trig. Okay, so here's an example. This is, if you have the textbook or if you have it in the future, here's example 1.5 in the book. Okay. A cross-country skier skis 1 kilometer north and then 2 kilometers east on a horizontal snowfield. How far and in what direction is she from the starting point? Okay, so we're gonna go through our process for solving problems that I outlined yesterday, that IC process. So the first step in that, remember, is identify. We want to identify what it is we're looking at and what our target variable is. Okay, so we're dealing here with displacements, or just distances, right? Not velocities, not forces, just distances, but in particular directions. So those are displacements. Okay, and we are looking for how far and in what direction she is from the starting point. So since we're looking for a magnitude, how far, and a direction, that means we're looking for a vector as well. So that would be our resultant displacement. So setup is our S, setup. I always recommend that you draw a picture of what you're given just to help you visualize things, right? So our skier is going 1 kilometer north and then 2 kilometers east horizontally. So we're not dealing with 3 dimensions here, just 2. And then this resultant vector, the blue one, is what we are looking for. How far she is from her starting point and in what direction. Okay. So we're going to use the Pythagorean theorem to calculate the magnitude, or how far she is from the starting point. So remember, we take those components of our vectors, and in this case, it's nice and simple because our initial direction north is right along that y-axis. So there's no crazy angle that we have to consider for that one. And our second direction is right along the x-axis, east. So again, there's no crazy angle to consider there. So we have our x component which is 2 squared, plus our y component, which is 1 squared. And then we take the square root of that. That gives us a magnitude of 2.24 kilometers. So that's how far away she is from her starting point. Can a magnitude be negative?
No.
No, a magnitude will not be negative, right? Because a negative tells us about the direction that it is going, not just the size. Okay, then we'll use trig to find the direction of the resultant vector. So if we remember from our trig function slide, right, here we have a right triangle, and this is the angle that we are interested in, because this is the angle that relates the initial vector to our resultant vector or final vector. So here's the angle of interest, and this Greek letter is phi. Okay, so this is the angle that we're looking for. Now, according to the triangle, the resultant displacement is our hypotenuse, because that's the longest side of our triangle. We don't know what that quantity is. Well, I guess we just found it, but if you had done the direction first, you wouldn't know what that magnitude was. So I would recommend that you stick with the things that you are given in the problem when possible, right? So we were given this length of the triangle, which is the side that's adjacent to our angle, 1 kilometer. And we were
Can I solve this?
Hold on just a minute, please. We were given the side of the triangle that's opposite our angle. And so remembering SOHCAHTOA, our trig function that combines the opposite and the adjacent side is tangent. Right, so that's why I've chosen to use the tangent here. So the tangent of our angle is opposite over adjacent. And we're looking for that angle. So to find that angle, we'll use the inverse tangent of the opposite over adjacent side. Okay, remember, our opposite side is 2, adjacent side is 1. So when we type that into our calculator, you get a result of 63.4 degrees. Now, you can use radians if you prefer to use radians, but just be aware of what the particular problem is asking for. It's possible that your professor might ask you how many degrees or how many radians, and you want to make sure that your calculator is set up for that particular unit. Victor, you are raising your hand.
Is there a difference between the symbol theta and the symbol that's there?
Yeah, so theta is like an oval with a line through it. I don't know that. I don't know how to do that with my fingers. So this one would be phi. There are all kinds of Greek letters that you will get familiar with throughout your course of physics.
But they serve the same purpose, right?
They serve the same purpose.
Okay,
Yeah, it's just
thank you.
an arbitrary angle variable. Yes, thank you. Kyle typed theta into the chat. So that theta that he typed is the capital theta, which looks very similar to the lowercase theta. Okay, so there's another question here in the chat. Would we also have to specify that the angle is 63.4 degrees north of east? You are definitely welcome to be that specific if you would like to be. But remember, it's kind of implied that our angles are measured like counterclockwise from east. However, in this case, our angle is not measured counterclockwise from east. So this angle right here is actually inside of our triangle still. So this angle would really be 63.4 degrees east of north, right? Because we were north, and now we're leaning towards the east by 63.4 degrees. Okay, does that make sense? Angles are a weird thing to specify in physics. Okay, so there are our final 2 components of our answer. Okay, so here's example 2. This is probably, we'll see. This might be the last example that we get to today, but we'll see how it goes. Okay, So after being left at home alone, Kevin McAllister realizes he needs a new toothbrush. To get to the store, he walks 9 blocks west and 3 blocks north. Each block is an eighth of a mile. After which he must take a 0.35-mile shortcut northeast through a park to avoid capture by the police. How far is he from home now, and in which direction should he walk to get back to his house as quickly as possible? Okay, so let's go through our problem-solving process again. So the I, identify. Okay. So what exactly are we looking for in this problem? Well, we're looking for how far he is from home. So his displacement, right? In which direction he should go. So not just his distance, but also his direction. So that's our displacement. Okay, so same sort of thing as example 1, we're looking for our resultant vector. So S, set up the problem. Again, I always recommend that you start by drawing a picture. So here's his house. He walks 9 blocks west and then 3 blocks north. And then he takes a shortcut northeast. So that's a 45-degree angle northeast through the park. We want to know how far he is away from his house and what direction he has to walk to get back.
How long is a block?
A block is an eighth of a mile. But yes, that is a
Oh,
very
whoops.
important question because we have mixed units in our problem. Right? Okay, so we have blocks and we have miles, but we have our conversion factor here embedded into the problem. Each block is 1/8 of a mile. So you can either make all of your distances in terms of blocks, or you can make all of your distances in terms of miles. It doesn't matter as long as your units are the same for all of your lengths. Okay, and there we have what we're looking for, the distance and the direction, which together give us the displacement. So looking at our units here, right, they're not the same. Here's my conversion. So if each block is an eighth of a mile, that means we have 9/8 miles. So 1.125 miles. And this distance is 0.375 miles. So now all our units are happy. The fact that he travels northeast through the park is important because northeast, just that direct northeast, that phrase implies that it is a perfect 45-degree angle, equal parts north and east, right? That same idea would apply to southwest or southeast or northwest, right? If you see that phrase with no other angle written with it, that is an implicit 45-degree angle. Okay, so let's start executing our solution. We know that to find the distance, we're going to use the Pythagorean theorem of the x components squared plus the y components squared. We don't know what those are yet completely. To find the direction, we'll use the inverse tangent of our y component over our x component. Again, we don't know what that is completely, so we need to find those first. Now we have this vector, which is off at a weird angle. It's not directly along one of these axis lines anymore. So we have to take this 0.35 miles and break it down into its components so that we can find out how much of it is horizontal along the x direction and how much of it is vertical along the y direction. Okay, so we see in the in the x direction, we have this 9 blocks portion, and we have this portion of our northeast, whatever that happens to be. Right? And we can see that those are pointing in different directions. That will be important. For our y components, we have our 3 blocks north, and we have whatever this component is from our northeast direction as well. So 2 components in the x direction that oppose each other, and 2 components in the y direction that are in the same direction, so they will add together. Okay, So here, if we look at this triangle for the portion, the vector that's off at an angle, we were given the hypotenuse of this triangle, right? Because that's the longest side. We were kind of given this angle of 45 degrees. So we know the hypotenuse and we know the angle, but we don't know the other two sides of the triangle. So we can use the sine of the angle to find the side that's opposite. Remember, so Katoa, sine is opposite over hypotenuse. And then we'll use the cosine to find the side that's adjacent. So Katoa, cosine is adjacent over hypotenuse to find that x component. Okay. So if the cosine of the angle is adjacent over hypotenuse, that's our definition that we saw on that previous slide, then the adjacent side is the hypotenuse times the cosine of the angle. Okay, similar for the sine. Now I'm going to establish our directions, which ones are positive and which ones are negative, according to what is pretty standard, right? So standard convention says that right and up are positive directions, or east and north are positive directions, whereas down and left, or south and west, are negative directions. Okay, so we'll keep that in mind as we do our math. All right, so here's our x component, both of them added together. So we have this negative 1.125 miles that he first walks. And again, that's negative because he's walking to the west. For this top triangle, he's walking back slightly east. So that will be a positive distance. And so that side is the hypotenuse times the cosine of our angle, 45 degrees. So that gives us an x component that he walked of negative 0.8775 miles. A similar process, that's the word process, for our y component, right? Initially, he's walking 0.375 miles north, so that's positive direction. And then he's continuing to walk north. The length of this part of the vector, this y component of the vector, is 0.35, the hypotenuse, times the sine of our angle. And so that gives us 0.6225 miles. So now we have our final x component and our final y component. Now we can find the magnitude or the distance that he traveled. So we take our components and square them, add them together, and then take the square root. So that means he's 1.076 miles away from home. To find the direction that he needs to travel to get back home, we're going to take the inverse tangent of the y component over the x component. And that gives us a negative angle, negative 35.35 degrees. Now, we do have to be careful here, beware the plus or minus 180 degrees, because there are two angles that will give you the same inverse tangent value. So we want to make sure that we're measuring our angles according to standard convention, which is from the positive x-axis. And so we need to really pay attention to what angles we're being asked to find here. Okay, so this would be the angle from the positive x-axis that is negative 35.35 degrees. Okay, so I see a question in the chat. Let me get that one first. Does that mean the angle between 3 block and 9 block is an implied 90 degrees? Yes, it is implied 90 degrees, right? Because going from west to north is a 90-degree angle in our axes. Okay, and yes, I saw another hand raised.
I was like doing my calculator,
Mhm.
and I times 0.35 times the sine of 45,
Mhm.
and I got like 0.247 instead of the answer that you had on the screen.
Is your calculator in radians?
Hmm. I'm not sure actually.
Okay, I don't have my calculator with me. It's out in the other room. But yeah, if you look on your calculator, I'll just show you my phone, for example. Okay. So this button right here, degrees or radians. Right now, my calculator is in degrees, but it could just as easily be in radians, and that would give you a completely different answer.
I
So
checked
yeah,
actually.
just something to be aware of. You want to make sure that if you want to report your angle in degrees, that your calculator is calculating in degrees. You can use radians too. It's just your answer will be in radians and not degrees, so it won't match mine completely.
I understand that, but my calculator is in degrees though.
Okay. Does anybody else have their calculator and is playing along at home? What answer did you guys get? Going once, going twice, anybody?
Hold on, I'm trying to figure out.
So can you remind me what answer you were getting?
I was getting 0.247.
Yeah, so that's for just that component. We're looking at the green one or the red one, I guess.
The green one.
Yeah, so that's for that component. And then when you add the 0.375, you should end up with 0.625.
Oh, okay. Well, it was just me then. Never mind.
Okay. But I mean, I'm glad that you mentioned that because that allowed me to point out the calculator caution. Okay. So the question in the chat, how do we find the formula for the X and Y components? So that would be these ones up here in the orange, I think. Yeah. I'm going to assume that that's the one that you're asking about. So remember, when we're looking for our final X component, we're going to add together all of the X components that we have for all of our vectors. So since this first distance that he walked is in the X direction or horizontal direction, we're going to consider that one in our X component equation, right? And the entirety of that vector, that distance, was in that direction. So we have that negative 1.125 miles. Okay. We also later on have the other component in the sort of in the X direction, right? Northeast. So part of it is to the east. And so we have to consider that portion of it as well. So we had two vectors where at least part of it was in the X direction. And so that's why we got two X component portions. And then the same thing with the Y component. We had a vector that was completely in the Y direction. And then we had a vector that was partially in the Y direction. So we had to consider that part that was in the Y direction as well. And so that's why we have those two terms there as well. Okay, hopefully that answered your question, Leah. All right. So we will stop here for today. I know I kept you guys about 5 minutes over. And then we'll start off tomorrow with a couple give it a try problems. Question in the chat, is there a bonus question? There is a bonus question. I can, well, not necessarily a bonus question. There are bonus activities. I'll say that. There are bonus activities that you guys can try. Let me pull those up for you real quick. Okay, so here are the bonus activities that you can give them a try. So these are going to help you with your trig identities, with your
Miss L.
One moment, please. There are these three files which should already be available to you. Okay, yes, do you have a question?
The screen, on my perspective, like the webcam, your webcam is switched with the screen and it's smaller. Is that just me or?
That might just be you.
Oh, it is me. Never mind.
Cool. Yeah, so here are these 3 activities that you can try. The first one is The Adventures of Shelley the Sea Turtle. So this one you'll need some additional materials, a ruler, a protractor, a large piece of paper, but this will give you practice drawing out your vectors, putting them tip to tail, figuring out where your displacement vector should be, that sort of thing. This other file, Vectors Trig Practice, you'll need a scientific calculator so that you can practice using those trig functions and figuring out the angles or the sides of a triangle. And then there are some additional book problems. These would be your more typical homework style problems from a professor because these are pulled directly from the textbook. So you'll need a calculator, possibly a ruler, protractor, or graph paper if they ask you to add or to diagram some vectors. But these are all available for you on Canvas. I'll be posting answer keys for all of these things on Friday so that you can check your work. But we will kind of, I guess, pick up where we stopped today tomorrow if you guys don't have any other questions.
Thank you very much. Bye.
Yeah, thanks. Have a great day and I'll see you guys
Thank
tomorrow.
you.
All right, thank you.
Bye.